Welcome to the video presentation of our letter, FlyOrb, Spherical Terrestrial-Aerial Bimodal Vehicle. In this letter, we propose a novel spherical terrestrial-aerial bimodal vehicle, FlyOrb, which enables both aerial flight and ground rolling with strong adaptability to complex environments. We use an inertial wheel resonance-driven strategy for rolling motion. For aerial mobility, we use unactuated hinges, where the arms are passively deployed by rotor thrust. The detailed hardware implementation is shown in the figure. When the arms are closed, the size is 20 × 20 × 20 centimeters, and when the arms are fully extended, it reaches 27 × 26.7 × 26.7 centimeters. The total takeoff weight of the vehicle is 1.17 kilograms. The mass eccentricity design makes the sphere behave like a roly-poly toy, which allows the vehicle to be self-stabilizing on the ground, but also makes it difficult to initiate rolling. Resonance-driven motion is highly efficient, with the applied force aligning with the velocity to maintain positive power and continuous energy input. We propose a resonance-driven rolling strategy for activation and efficient rolling. Videos and graphs demonstrate the simulation and experimental results of resonance-driven rolling initiation, with both showing good agreement. The energy variation curve is obtained through simulation. As a result, the kinetic energy briefly increases when the potential energy V reaches its minimum at the equilibrium position. Moreover, the vehicle's motion patterns on slopes and steps are further analyzed. As shown in the left figure, each slope angle corresponds to a curve, and the colored area shows the feasible rolling region for slope ascent. As shown in the right figure, the yellow overlapping region of these two areas indicates that FlyOrb can roll over the step. We also carried out force experiments on the propellers across different configurations. Without arms, the thrust follows F equals 0.824 times omega squared. With arm 1, the thrust follows F equals 0.423 times omega squared. And with arm 2, the thrust follows F equals 0.719 times omega squared. Therefore, arm 2 has better aerodynamic efficiency compared to arm 1. FlyOrb's arms connect to the body through unactuated hinges. Through derivation, we can obtain the feasible range of total thrust and yaw torque when roll and pitch torques are zero. The green feasible region B with unactuated hinges is a subset of the red feasible region A with rigid arms. As a consequence, the use of unactuated hinges weakens the flight maneuverability. Finally, we conducted prototype tests. During takeoff, FlyOrb unfolds its arms, and the deployment time of the arms is 0.82 seconds. It performs stable flight movements similar to those of a quadrotor drone, and the arms automatically fold up after landing. When rolling, it first initiates motion through resonance-driven rolling to overcome the highest point of potential energy, and then continues rolling continuously. The average rolling speed is approximately 0.35 meters per second. Thanks for watching.